Okay, we're looking at a video from a camera supposedly mounted on the lunar module looking down on Apollo 11. This would be Neil Armstrong and Buzz Aldrin. Now, there are a few things I would like you to notice here. And first, notice that nowhere in this video is there any evidence of 1/6 gravity. Also notice that the astronauts are walking around in an almost complete upright position, completely vertical. It's almost like they're walking down a sidewalk here on the Earth. And also notice that even though this is the first time that men have ever walked on the surface of the moon, they are very comfortable doing this. There is no evidence at all of any slipping, sliding, no loss of balance, no trying to catch their balance. There's no tripping, no falling. It almost looks like they're on just walking around on a desert area here on the Earth. I contend that what we see in these videos and photos is physically impossible. We need to understand how we are able to stand upright and keep our balance. There are a few key concepts to understand: center of gravity, base of support, and friction force. We need to look at the physics of the force of friction and how friction helps us to maintain our balance, and we'll take a look at a martial arts video that does a great job of explaining center of gravity and base of support. Now here we have a small man and a much larger man, but the small man is able to throw the large man over his shoulder. And he does that because he's able to pull the center of gravity of the large man off his base of support. Now the center of gravity is that point in any object where you can balance that object in any orientation. And here we see that the base of support is that area between your feet. And if the center of gravity is right in the center, that is when you would be at your most stable. And he pulls the large man, the center of gravity, off of his base of support. At this point, the large man is unstable and will fall over. And then he flips him, the large man rotates him about the center of gravity of both men as a fulcrum and a lever. And of course, the farther out on the lever that he's able to exert force, the less force is necessary. And he has the large man by his hand, his arm, so it doesn't take much force to rotate the large man around the center of gravity of both men, and he can easily throw the big man over his shoulder. Now here we have a representation of the center of gravity over the base of support. Now, when the center of gravity is right centered on the base of support, that is when you are perfectly balanced. Now, if the center of gravity is off of the center of the base of support, you can still stay upright and balanced if there is enough friction. But once you start to move your center of gravity off of the center, off to the center of the base of support, you start to create an imbalance force. But as long as there's enough friction, you can stay upright. Once your center of gravity is off of your base of support, then you'll fall over. Now here we have an excellent representation of, here's a man in a horizontal, balanced horizontally, and you can see that his center of gravity would be right in here, right above his waistline. His base of support is just the area of his hand, and he has to have his center of gravity just centered perfectly to be able to balance like that. Now here we're looking up at a person from the bottom of their shoes. Now this the area within the dotted line would be the base of support. Now the center of this base of support would be the spot, the perfect spot where you would be, if you could keep your center of gravity right over that spot, you would be in perfect balance. Now, if you're on a slippery surface, as long as there's enough friction, you can move your center of gravity anywhere within this base of support and you can stay upright. But what happens is, if you don't have enough friction, your base of support essentially shrinks. And if you have a very slippery surface, like wet ice, for example, your center of gravity needs to stay in a very small area. If you're outside of this area with your center of gravity, there's enough imbalance. You get a cantilever force against the side of your foot, and that force will cause your feet to slip and you'll fall over if you do not have enough friction. Now, as long as your center of gravity is on your base of support and you have enough friction, you can stand upright. Now, here's a good question. Could you stand upright on a perfect frictionless surface? Well, the answer is no, and I'll talk more about it in maybe another video. But you could not stand upright without friction. That's how important friction is. Okay, now it would be difficult for the Apollo astronauts to stand upright on the moon, even if they weren't unencumbered by their life support system. But they had this huge contraption on their back, and we'll take a look at that. Okay. This is the life support system that was on the back of the Apollo astronauts. It consists of oxygen tanks, primary and secondary oxygen tanks, and a lot of stuff here, motors, pumps. Now on top of this, the life support system weighed about 80 pounds or so. And then on top of this is the backup system, the oxygen purge system. It weighed 40-some pounds. Between the two, about 125 pounds. And then that was empty. You had to have oxygen tanks. You had to put water in this thing. A gallon and a half of water, supposedly. And then you had lithium hydroxide cartridges to scrub the carbon dioxide out of the recycled oxygen. And then batteries. Now in 1960 technology for batteries, I'm sure the batteries would have been very large and very heavy. So depending on what sources you look at, this whole apparatus weighed as much as 180 pounds. And here's another look at it. Now this is just the bottom part, the PLSS, the primary life support system. And you can see it's quite an awkward thing to have sticking over your back, hanging on your back. And this is the top part, the OPS, the oxygen purge system, which another look at it on top, another 40-some pounds. Now, I think common sense tells us that if we have a 180-pound backpack on our back, that we won't be able to stand upright. Now I know we're on the Earth now, 180 pounds. And we would need to get the center of gravity of our body, our upper part of our body, over our base of support. And this is how we would have to stand with that kind of weight. Now I know what the argument is going to be. On the moon, this will weigh less. And I think people dismiss this when they see the astronauts on the moon walking about. They dismiss this fact that this backpack is so heavy, but it's a false dismissal because it is not the magnitude of the forces that is important. It is the relationship of the forces to each other. It is the ratio of the forces that determine if a man can stay balanced upright or not. This ratio relationship would be the same on the moon as on the Earth. If you are in balance on the Earth, then you are in balance on the moon with the same equipment and posture. Consequently, if you can't stand upright on the Earth with a heavy backpack, then you can't stand upright on the moon either. And you know what happens when you put too much weight in your backpack and you stand upright? We need to talk about friction now. Okay, here we have the force of friction. Frictional resistance to the relative motion of two solid objects is usually proportional to the force which presses the surfaces together, as well as the roughness of the surfaces. Okay, now we're interested in our formula here, right here. The force of friction is equal to mu, the Greek letter mu, which stands for the coefficient of friction, times n, the normal force. Now mu is usually a number between 0 and 1. In other words, mu is a fraction. So it's a fraction of n, the normal force, and the normal force is simply the force pushing down on the surface. Now if you're a person standing up on a surface, n, the normal force, would simply be your weight. So the force of friction is a fraction, the coefficient of friction, a fraction of your weight. The slipperier the surfaces, the surface, the less the force of friction, the less the coefficient of friction would be. Now, here we have the coefficient of friction for the substance rubber on various surfaces. We have rubber on concrete all the way down to wet snow. Now we're interested in rubber on dry gravel because this would be similar to what the astronauts, the Apollo astronauts, would have experienced on the moon. Their boots on dry gravel. And the coefficient of friction is somewhere between 0.4 and 0.85. Let's average this out to about 0.6. And also notice down here, rubber on wet ice, 0.05 to 0.1. Let's call it 0.1. So we have rubber on gravel, 0.6, rubber on wet ice, 0.1. And this is a ratio of 6. This means that there is 6 times more friction of rubber on gravel than rubber on ice. On the moon, there is only 1/6 the gravity of Earth, so there's only 1/6 the friction holding a man in place. This means that standing on the moon would be like standing on wet ice here on the Earth. It would be very difficult to keep one's balance. Now think about that. Standing on the moon is like standing on wet ice. And it's very difficult to stand on wet ice, isn't it? Even NASA's moon gravity simulations filmed in the 1960s show this reduced friction effect, the slipping on ice effect.
On the right, see in starting and stopping his movement due to the low foot traction resulting from the subject's low apparent weight. Similar difficulty is encountered by attempting to run. The degree of difficulty will vary with both the type of footwear and the type of surface used on the walkway.
Even if you have 4 legs, it is difficult to stand up on wet ice. Now, this image of an Apollo astronaut is impossible. Even if the force of friction is not the equivalent of wet ice, if this astronaut was standing on dry concrete, this image would still be impossible because his center of gravity is off of his base of support. He could not stand like this. It is impossible. I think I'll end this video with a great quote from that remarkable detective, Sherlock Holmes. And here is what he had to say about the impossible.
The door is locked, the window inaccessible. The grate's too small. How then?
You will not follow my precept. How often have I said to you that once you have eliminated the impossible, whatever remains, however improbable, must be the truth.
I'll let you judge for yourself what the truth is. And thanks for watching.